it's not mirroring it or anything. So
Well, oh, okay.
I'll work. So if you want to like reserve all something in there, we're good to go. Here. Oh, thank you.
Yeah.
And it went to move it. Oh, there we go. Come back up. Okay. Oh. Come on, new display. There we go.
Okay, that's fine. Same thing.
It's always possible to, you guys there, so it's go in the hall and
sorry. 4% in 4 minutes. Not 4, 10 minutes. Right, I'll take it. Why take it?
Please. Next on the schedule is Florian Westphal, and we'll be speaking about Data Center TCP.
Yes, thank you. So actually that's a bit of a lie, because I'm not only speaking about Data Center TCP. A large part of the talk will be Data Center TCP. But unfortunately, to really explain how it works on the inside, we will first have to explain some of the underlying technologies that it uses. So namely, we will shortly explore explicit congestion notification. We will look at how buffering happens in the network. And since Data Center TCP is mostly about congestion control, and we will have to first find out what congestion control is. And so let's first have a look at ancient times when the first TCPs were deployed. Then we will discover that there is no congestion control at all. And if you look at the original RFC, it will basically say in some language, yes, sometimes packets will be lost because the network is congested. And then we will simply retransmit and packets will be delivered. If you have data to send, then basically what TCP does, it looks at how much the peer is willing to receive. That's the receive window, which is announced in the TCP header. And then you look at how much data you have, and then you send a smaller number of the two. In 1986, that went bad. There was the so-called congestion collapse. And what that means is that most packets in the entire network were only retransmit. And you could basically no longer create new connections, and existing connections came to a grinding halt because the nodes reacted to the packet loss by doing an immediate retransmit, and again and again and again. So there was no backoff at all. And that's exactly what was added to the protocol, or rather not to the wire format. It was kept backwards compatible because it's a sender-only modification. So essentially what we do, we add a third variable to the equation. So we not only look at the number of bytes that we have to send and at the number of bytes that the peer can receive, but we have a third constraint, that is the so-called congestion window, which is basically our own view of the network, how much the network will be willing to accept. And this congestion control also introduces two main phases, and that's slow start and congestion avoidance. And if you look at some classic congestion window moderation algorithm like Reno, then it will usually look exactly like that. So you have a fast ramp-up phase where we start slowly. That's why it's called slow start. And then for every packet that is acknowledged, we will increase the congestion window. So we have a really, really fast phase. So it's 2, 4, 8, 16, and so forth. And that continues until we reach a point that's the so-called slow start threshold. And then we leave this phase and we start a more conservative approach and just increase the congestion window only very slowly, because we think that we are close to essentially maxing out the capacity of the network. And whenever there's a packet loss, then we will halve the congestion window and start anew. So that's why you get the sawtooth behavior. So every time there is a dip, and you can see that on the slide, that means there was some congestion event or some packet loss event, and we are retransmitting. And at the same time, we are being more conservative in what we try to push onto the network at once. And by that, we ensure that if the network is congested, the nodes will actually start to slow down and not cause even more problems. if you look at this closely, then unfortunately it's not as simple as it sounds, because it's not trivial to decide when you grow and shrink this congestion window value. For instance, if we say that we increase it for every round trip time whenever we have an acknowledged packet, and your link has, let's say, half a second of delay, then it means that it takes a very, very long time until we ever reach a maximum value, just because we always have to wait for an entire acknowledgement to come back. Another problem is that packet reordering in the network is a reality. It just happens on the internet. So even if you think that if you receive duplicate X, it might indicate a packet loss, it's not necessarily that a packet loss even happened. It's entirely possible that the packet that you've sent is just still on the wire and hasn't arrived at the destination yet because it's coming out of order. And more complicated is even if you know that a packet has been lost, then it's not necessarily due to congestion. If you think, for example, of wireless networks, it's simply possible that there was some interference and the packet got discarded at the other end because it had a bad checksum, for instance. So in that case, you would not want to reduce the congestion window because there is no congestion, but you can't know. So on top of that, the available network capacity obviously always changes because it depends on how much data other senders are pushing onto the receiver and on what links you have and things like that. So this is a very active research topic, and there are literally dozens of different algorithms. In Linux, congestion control is therefore put into some framework. So congestion control is not even part of the core network stack. Instead, the core network stack will, at some particular places, it calls hook functions of a congestion control module that is always assigned to a TCP connection. You can, for instance, the default is cubic, which is kind of one-size-fits-all solution and tries to be fair in all possible scenarios. But for instance, if you have some particular knowledge of your network, like it's a wireless network, then you can change that to a different algorithm like Vino or Hybla, which have different properties. For instance, Hybla is especially designed for satellite networks where you have very long delays, so it will not put extra penalties on connections that have such high delays. And the network stack will not really care what the algorithm does with the information. It just says something like, okay, I've just sent a duplicate ACK, or packets have been lost and I'm now recovering from the loss, and the algorithm module will do something with that. You can change the congestion control algorithm via syscontrol. That's the global configuration. Starting with 320 kernel, we will also have a per route setting, so you can have different settings for different networks. And you can even, if you're a programmer, you can even change it programmatically per socket via set-socket call. And as I said before, you can mix the algorithms. You can have, you can basically use all the 12 or so algorithms that we have in the kernel at once, but just one algorithm per each individual connection. So, next up. So we have seen that there's what congestion control is. Now let's have a look at what a network actually does with packets that are flowing on the wire. If you look at a very, very simple setup, for instance, we have two senders and a single destination, and the senders start to cram packets down the wire onto a single router. Then once we have more packets arriving, then we can send out. A queue will form. This is quite natural and shouldn't we have to explain anymore. It's basically similar to traffic light or whatever. Once the arrival rate is too big or bigger than the departure rate, you have a queue. Instinctively, you would say that you would just buffer as much as you can, but it turns out that this is not really the best solution. And in fact, TCP senders are confronted with a couple of problems with queuing. Most notably, if the buffers are too big, then it will take the sender a very long time before it realizes that a congestion event has even taken place, because all of the packets are still sitting in some queue. It has to wait until all of those packets some of them have arrived at the destination, and then by lack of acknowledgements it can infer that a loss has occurred. But that's not what you want. You would actually want that the sender knows soon that some overload situation is imminent, so it can throttle down. On the other hand, if you make all the buffers very, very shallow, then you will have a problem once there is this short burst, because then you will actually drop packets, even though the event would have been very short, and with just a few bytes of RAM more, you might have been able to just queue it so that no packet loss is induced. And lastly, the very simple let's just drop once all the buffers are full is also not very good, because if you just drop at the tail, so you try to buffer as much as you can, and then when you're out of space you start dropping, that works. But the problem is that if you do that, then you're basically guaranteed that you will affect many, many flows at once. And if you now remember the sawtooth line of the congestion window graph that I've shown on the first slide, the problem with that is that then a lot of flows will experience exactly this graph at the same time. So they will all back off at the same time, they will all start to increase at the same time. So your network utilization will be very uniform. It will not be very uniform. It will go down all at the same time, and that's not what you want. Basically what you want is that all of your network is reasonably well paced, and you have some good distribution of data. So our wish list would be for the network: we want to know about the loss as soon as possible, and we want the network to be smarter about how it manages the buffers, so that once buffer, for instance, what you can do is once the buffer starts to fill, but you still have plenty of room left, you just randomly discard packets. This seems very strange, but when you think about it, what will happen is that only one signal, namely the affected flow, will start to throttle down, and the others will not. So you will not have this problem that all of them back off at the same time. There are a couple of algorithms in the Linux kernel that do this, for instance, stochastic fair blue and Coddle and choke and a couple of others. We will not look at them here. But most important of all, and that would be the best, if we could detect that congestion is imminent even before the loss event occurs. Because when we have a packet loss, we will always have to do a retransmission. And if we could avoid that and just throttle down before any loss occurs, that would be the best. And in fact, there is a technology to do that, named Explicit Congestion Notification, which is an extension to the Internet Protocol that allows a router to, instead of dropping a packet, it sets a special magic flag in the packet header, so that when the packet arrives on the other end will see, okay, one of the paths on my network is experiencing congestion. The good thing about this is that we have a clear marker that will tell us that congestion is imminent, and we won't have the ambiguity that packet loss has, because packet loss can be anything and not just congestion related. But one of the problems with that is, of course, that a sender can do something about it, but not a receiver. So we are only halfway through at the moment. We have set a magic marker, but only the receiver knows about it, because it can look at the packet, but the sender not. So we have to plumb this to TCP somehow. And that was done by adding two new TCP header flags, namely ECE and CWR. So what happens is, if this extension is negotiated during the three-way handshake of TCP, then what the receiver does is, when it sees this magic marker in the packet header, it will raise this TCP flag ECE in the next acknowledgement that it sends back to the sender. And the sender can then see that. It can do the congestion window reducing without having to retransmit anything because there was no packet loss. And it can then inform the receiver that it took action by sending this action to prevent further congestion. You can enable this extension on Linux via a system control value or either on a pair route setting, which will also be in the 320 kernel. Now, one question is, if this is so great, where's the problem? So the problem is, as usual on the internet, it's middle boxes. There are lots of middle boxes that do strange things and bad things. And basically, if you turn on ECN on the internet, then you will about 0.5% of sites will be invisible to you because they are behind firewalls or some other middle box that drops packets, TCP SYN packets where this I want ECN marker is set. So you have a black hole problem. The second problem is, even if you don't have a black hole and you can and the three-way handshake passes, there are broken switches and routers that will assert congestion experience marker for every packet. And when that happens, then of course your performance goes down the drain because your sender always thinks that the network is congested, and the congestion will basically always be 1. And sending one packet and then having to wait for an acknowledgement, that of course takes forever. So, and even if the signaling would work, proper marking currently, unfortunately, virtually never happens. So on the internet, it pretty much has absolutely no advantage to turn it on. Another problem in its design is that since it's just a single marker bit for congestion experienced, it doesn't tell you the extent of the congestion. It just says that there is congestion, but not how much. So all in all, it's always default off. So to summarize that a bit, the current TCP stacks are very good at detecting loss and retransmitting packets really fast again. But of course that's still bad for latency because we have to wait until the packet has been retransmitted before the receiver can actually proceed. The good news is that this extension is present in all the major operating systems and in all the current generation switch firmware. It's just problematic due to the myriad of bugs and legacy implementations out there. On the other hand, of course, if you have full control over all the nodes involved, like in a data center, then that changes because you can just throw out all of the middle boxes that cause problems, or even better, just design it from the ground up that you know that all of your involved systems will do the right thing. So we have learned all about the underlying technology, so finally we can switch to a Data Center TCP and figure out what's it doing with all of that stuff. So first of all, there are 3 main requirements for data center traffic. That's high burst tolerance, because usually you have a lot of machines and a lot of switches and they are interconnected somehow. So it's unavoidable that sometimes you will have several dozens of machines sharing the same switch because they have to go through the same bottleneck. The second one is you want low latency because you might have search engine queries or some other interactive traffic request response type things that you want to be resolved as soon as possible without delay. On the other hand, you always have the requirement you want also high throughput, for instance, because you have some network attached storage system and that's also being used. So you want basically all of those 3 at once. And Data Center TCP tries to accommodate that. And it does that by leveraging this explicit congestion notification to also estimate the amount of bytes that are congestion. And based on that, it will try to do this congestion control. So the idea is that every switch or router on the data center will be configured to start marking packets once you go over a very, very low threshold of buffer size. Usually it's about 100 kilobytes only. So as long as the queues are really shallow, nothing special happens. Once it goes above that limit, it will just always mark the packet. That has two effects. One, we learn early when buffers start to fill up. And the second effect is we have burst tolerance, because if there is a burst of packets, they will not be dropped because there is still plenty of space in the switch or router buffer. Data Center TCP tries to estimate the amount of congestion and not only the presence. And it does that by introducing a so-called observation window, which basically consists of the unacknowledged number. That's basically the packets that you've sent, but you don't know yet if they have been received on the other side, and the next sequence number that you're going to use when sending a packet. And it has counters for marked and for the total bytes. And for every acknowledgement that you receive, you will check if this ECE flag is set. That is, if the peer says it got marked by a switch. And if it has, you will count it as both in the total count and in the special marked counter. And if it's not ECE marked, then you will just count it as a total. So you can compute a fraction of the marked packets simply by dividing the marked packets with the total count. And based on that, you can then compute a value that is called alpha, which is essentially the amount of congestion that you believe is active is present in the network. And this observation window will be shut down once the next send window is acknowledged. And then if the entire process is simply restarted. All the counters are reset and it starts anew. There are some tunables here. For instance, you can influence the number of wait that you want to give to the current window. So if you set this indicator very high, then you will prefer the latest measurement that you've taken, and if you put it very low, then it will take longer for this alpha value to converge towards the ideal point. So it's a bit of a trade-off. The default is a fraction of 1/16, and that's also what's used in the Linux implementation. It's based on the original Stanford paper. So as I already said, alpha represents the fraction of the marked packets. And then the congestion window can be computed simply based on the old one, or the previous congestion window, and the alpha value halved. The effect is that if alpha is close to 0, that basically means you have no congestion, and if it's approaching 1, that means basically that all the packets that you have received are marked and the entire network is congested. All of that, of course, depends on very realistic. It depends on the marked bytes. So the question is, how can we actually infer when a packet was marked? Because acknowledgements are usually not per packet, but it's typical that a receiver that has just gotten a few new packets will not acknowledge them right away, but it will simply wait a bit more and see if more data comes along, so it can do a cumulative ACK and just send a single ACK to tell the sender that everything was accepted, rather than generating one ACK response per received packet. So the simple solution would be just to do that, and for every packet that we receive, every new packet that we receive, we would send an acknowledgement out, and another acknowledgement, and so on and so on. But of course, that would mean that we send one ACK back per received packet, and that's something that we should really avoid, because it would increase the network load. So what Data Center TCP has, it has a, don't be afraid, it's not as scary as it looks. It's actually quite simple. Most of the time we will be in the CE0 state, and we will just do completely normal ACK processing like with any other TCP stack. The only difference is basically when we start to transition out to the CE1. So whenever we receive a packet where we see that the switch has set at the congestion experience bit, then we will immediately send out an ACK for the old data, and we will change state. That we will remember that a switch has told us that it is congested, and then for every new ACK that we send out, we will simply set this ECE bit in the TCP header to inform the sender that the current data that it's sending is always being received with a marked indicator. And once we receive a packet that is no longer marked, the inverse happens. We will send out a quick ACK for all the data that we already received. We will sort of flush out this bit. So we will tell it, hey, all the information that we got from you, we've got it, but it was received with a congestion experience indicator. And that's pretty much it. So we will do completely normal ACK processing. We just do some extra work, namely sending immediate ACKs if and only if the state changes. So in basically all the cases, it should always be normal ACK processing. The implementation in Linux is, you've guessed it, simply a congestion and control module. We had to extend the core network stack slightly to provide a couple of more events, particularly related to the CE marking bit, so that congestion control modules know when such an event has happened. We also introduced the ability that a congestion control module can say that it depends on ECN being available and otherwise will not work. This is why it's enough to actually configure DCTCP on a socket or a network. You don't have to worry about also tuning the ECN system control value, because it will be enabled under the hood for that connection. So the only problem left is that what happens when you create a TCP connection and the peer says that it doesn't support ECN. And in that case, it will simply fall back to the standard Reno algorithm. Not because Reno is particularly good, but we just do it because Reno is kind of a standard fallback that's always present in the kernel, and we don't have to mess around with module ref counting on qubit, for instance. So something about operation. First of all, there is documentation available in the kernel source tree. And while you can indeed enable DCTCP globally via the global system control value, please don't. It will not really work because as we have seen, it completely depends on ECN marking, and that doesn't work on the internet. So my suggestion would be to only enable it for your local network, and only if you have configured all of your switches and routers to mark as required. So finally, some words about debugging. We do have support for DCTCP also in this sockstat utility. So if you run the SS tool, it will list some internals about the DCTCP state machinery for those connections that are covered by that algorithm, and you can spot some problems using that output. So for instance, if it doesn't say DCTCP in the output, then that connection doesn't use DCTCP, so maybe you have forgotten to turn it on, or could be that you have to restart a particular program because its connection was already established, for instance. If you see something like fallback mode in the output, then that means while you have enabled DCTCP, the peer doesn't support ECN, so we had to do this Reno fallback. You can also see the alpha value, that is our idea of how big the congestion is in the network. And if that's always very, very large, then there's probably some broken middle box in your network that is just marking everything. this is the marketing slide. So we did run tests in a data center deployment, and as you can see, this is the same test actually. So even while you are doing a throughput test, latency is very, very low in DCTCP, simply because, as we have seen, the buffers in the switches are very shallow, and marking happens really, really soon after just a few kilobytes. So buffers are short, and that's why the ping times are so low, because the ISMP packets don't have to wait forever in the switch until they can be transmitted. And for the throughput, you see that the mean throughput is pretty much the same as cubic. That's not really surprising. We can't go faster than what the wire can do. But what you can see here is that the mean derivation is very low. So while the minimum transmission speed measured for cubic is just something like 400, it's just very short of the median for DCTCP. So you have a much less variance in the individual tests. That was done with about 19 senders in parallel, and while running ICMP pings in parallel. So basically the only issues with DCTCP are the configuration overhead, because all of the intermediate switches and routers have to mark. Then another problem is that if you have packet loss on a network, that will be very problematic, because Data Center TCP's congestion estimate depends on clear ECN feedback via the acknowledgement packets. Otherwise, the state machine breaks down. Because if you say someone sends 10 packets and 2 of them are marked with the ECE echo bit, and those 2 go lost and are not received at the sender, then the sender thinks that there's no congestion. And if 2 packets are dropped without the ECE bit, then the sender will overestimate the amount of congestion in the network. So that's pretty bad, but fortunately in a data center, pure ACK loss on the reverse path should be extremely rare, so it doesn't happen. It doesn't matter in practice. Another problem is that the original Stanford paper and the IETF draft of the protocol design are a bit fuzzy on some of the details. For instance, it doesn't say anything about whether we should adjust this congestion estimate value when packet loss is confirmed. And it doesn't say anything if we should adjust it when the link is idle. So say the link is idle for a minute and we send more data. Should we just use the last estimate that we had, or should we start like it was a new connection? It doesn't say anything. So we added a couple of tunables to the module. So you can currently set something, so you can set a parameter that's called clamp alpha on loss, and if you do that, then packet loss will be taken as an indicator of extreme congestion, and then the alpha value is always set to maximum. But it's off by default at the moment. Because, as I said, in a data center, if you have permanent packet loss, then something is completely wrong in your network anyway, and so it should not, it pretty much should not happen in practice. At least not as a congestion indication. So, any questions? Nothing? No one asks why you must separate DCTCP and TCP traffic on the switches? Because I forgot to mention that. And it's on the slide. So can anyone guess why you have to separate it?
You're going to tell us, right? You're going to tell us?
Yeah, I'm going to tell you. The problem is basically that if you start to mix it, then it depends on what your switch is configured to do. Because for a legacy TCP, the switch will not be able to mark because the packet will not have the bit set that says I understand congestion notification. So you have 2 choices. Either the switch is configured to drop the packet, in which case the performance of legacy TCP will suck because the buffer size is basically clamped to just 100 kilobytes and it will not be able to accommodate any bursts whatsoever. And if you do it the other way around, namely you just queue the packet, then what happens is that legacy TCP will drown out DCTCP completely. Because DCTCP will start to see mark bits, and it will throttle down because it adjusts the congestion window. But the legacy TCP senders, they don't know anything about congestion because all of their packets are being forwarded just fine. So they don't throttle down, which makes the problem even worse on the DCTCP side because even more packets will be marked. And so you will end up with 95% throughput for TCP and nothing left for Data Center TCP. So you pretty much have to tell the switch to handle them differently by, say, having a special queuing disk for TCP that will do standard read or FQ call active queue management for the legacy TCP traffic, so that some of their packets will be dropped so that they will slow down. So, yeah.
There's some kind of support, but does it make sense to enable it in a virtual machine, even though the bare metal does not support it?
Yeah, well, it depends on.
Suppose we have a KVM,
Yeah.
or does it require that the KVM network stack is informed about congestion from the bare metal?
Yeah. So basically, what you would have to make sure is that any virtual router or virtual switch in the path will honor this bit. If it doesn't do that, then DCTCP won't work because it will never receive any congestion feedback.
Is it the case, for example, with the Open vSwitch?
You will have to ask the Open vSwitch guys, I have no idea. Does anyone of the Open vSwitch experts in the audience know? Doesn't look like it. Sorry. Yep.
Do you know of anybody using it?
Yes, I know of.
production? I mean,
Yes.
but not in the node DC, basically, probably a greenfield DC built up from the scratch, right?
Yeah, pretty much. Yeah.
Okay. There's no way to retrofit this with.
Yeah, one company that uses it a lot is Microsoft.
Yeah.
They use it in their data centers, especially for the Bing search engine.
Any conflict with PD?
What?
Any conflict between DCTCP and SPDY? SPDY?
No, because SPDY is a much higher level protocol, so it doesn't matter. Or do you mean Quick, I think it's called, which is based on UDP? Do you mean a protocol based on UDP? I think it's called Quick.
Google SPDY for
Okay. Okay, thank you.
Hello. I want to ask if the marking on specific buffer length is it supported by hardware producers like network
Yes,
hardware producers?
the newer generation switches all have PQM support. Yes, you can consider it.
Yeah.
Last
violation?
Don't worry, you will get a bottle of water as a refund. Yeah.
My whole hard drive being rooted.
Come on, that's a Reddit sign.
I don't know how it works.
Yep.
Wait, so you want the ODP or the PDF?
Sorry?
You want an ODP or PDF?
I guess PDF would be better.
Okay.
They will basically, you know, on YouTube, it will show the slides as well when it's recorded. So.
It has, what's lame about the PDF is I have the animation crappy thing in there. So it's gonna be,
You can put them both there. And
it's okay.
very handily. PDF or OIF. Whatever.
Já si myslím, že PDF stačí.
Okay, thanks.
Now, is this going to work? Who's the expert on this stuff? I always tend to break stuff.
It should just work. There you go.
And you should see it also over there.
Awesome.
Laser pointer.
No, there is no one.
What?
Yeah, I know.
I really needed one. It was like...
Well, actually, I can try ask the technician guy, but I don't think so. There is.
Go ahead.
Oh, how about a long stick? It sucks.
Or long arm, you know.
Yeah, it's all about the arm.
You're quite tall.
Lack of laser pointer.